Alright, so all kinds of stuff to go through today. So I want to do a post-mortem on PA1. I want to talk about PA2. I want to talk about the ODPs, including the ones that I wasn't here to discuss with you, but that people seem to have good luck with anyway. I want to talk about the quizzes, and then maybe we'll actually talk about some data structures. So PA1, I got through all the assignments, I graded them, and they look good. So I think people are mostly in good shape as far as linked lists go. Hold on a second. So I think people are in good shape as far as linked lists, which is really important because PA2 is almost exactly like PA1. It's the same data structure we're working with. It's a different implementation of it. Same main program, same goals and requirements, but we implement it in dynamic memory instead of an array. So we'll talk about that today and tomorrow. I pushed back the due date on PA2 to a week from today because I wasn't here Friday and I wanted you to have a week after we talk about the basic assignment. This means that when you turn it in next Monday, you probably won't get it back in 24 hours, okay? Because I teach until 4 and I have something else at 6. And so it's probably going to be a few days next week before you get turned around on PA2. So just a heads up on that. So let's talk about PA1. So first thing was make files. So most people included a make file, which is good. A few people didn't. But you wanted a make file, and your make file can be pretty simple, right? But if you're breaking your code into pieces, your make file can do more than just say GCC all my C files together into an executable. So here's a pretty straightforward make file for the code that I'll go through in a little bit. I have a program, main.c, process.c, ll.c, and usage.c. I broke my code into 4 pieces. And to make the executable, right, I need all of these objects, these compiled versions of my C codes to be up to date, and if they are, then I can use this command. So GCC is a compiler. This says my output file should be called main. Okay, the output of GCC is an executable program. I use that term output file a lot. What I mean is a program that I can type the name of and it runs, so MAIN, right? These other things, main.o, those are compiled C programs, but they're not executable. If I say main.o, right, it's not even set to be runnable. If I make it runnable, and I try to run it, it says it's not an executable file, right? So those are objects when I'm compiling to make an executable called main. Where does this object main.o come from? It comes from main.c and mystuff.h, which I compile like this. We don't name the .h file when we compile, right? We don't name stdio.h when we say GCC. Don't name mystuff.h either, whatever your include file is called. And the whole reason for this is if I do something like modify a file like usage.c and I say make, it doesn't recompile all of my C code. It only recompiled one of my C files, which was the one that I updated, usage.c, and then it linked all the objects together. So if you're not clear on makefiles, take a look at the video I posted on Canvas. If you're still not clear, come and talk to me or ask questions in class, and make yourself a project with a few pieces and play around with makefiles. Pretty much any other course you take in C, you're going to be expected to deliver a makefile along with your program. The downside is if you don't have a makefile in there, and this is all you've got, how does a person compile your program to make an executable they can test? Well, they'll probably compile all the .c files together, but maybe you've got 3 versions of your add function that you were developing. And if you just compile everything .c, you're going to get compile errors. And so if you're supposed to have a makefile and it's not in there, chances are you're going to end up with 0, right? So I'll work with you, and I'll say, okay, well, I know how to compile this, right? But as you move on, so a lot of what we're doing here is trying to get you ready for transfer to a university. And university, you might have, 100 people in your class, and you have 3 TAs who are grading your assignments. They're going to say make if it says, compile error, it's a 0, they move on to the next one. They get done quicker that way. So makefiles are something to work on. If you didn't nail them in 224, keep working on them and ask questions about it. Let's talk about commenting. Okay. I'm going to start getting more serious about commenting requirements. So I've said you should have a comment block in the beginning of each function that describes the name of the function, what it's doing, what its purpose is, what the inputs are, what the output is, what the behavior of the function is, any side effects. What I'm seeing in a lot of cases is, integer add, parentheses, blah, 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 comment add, or maybe add function. Okay? That's not sufficient commenting. That does not tell somebody looking at this, what does this function do? What are the requirements to use this function? I'm passing it a number. The number is being added to what? To a linked list whose sentinel node is being pointed to by this first argument. Can I pass it a number that's already in the list? I don't know. Let's check the comments in the beginning of the function. What do they say? Add. Well, I don't know. Now I got to go through the code and figure that out, right? So even if you write really clean code and use really good variable names, you still need a lot of commenting, okay? And doesn't matter if your code is completely self-explanatory. Every class you take in programming, your teacher is going to insist on commenting, and the amount of points you're going to lose is going to increase to the point where in some classes, if there's not enough comments, you'll get a 0. So it's a habit to get into, right? And when you leave school and you go into the workplace, it's going to be the same thing, because your code is going to be looked at by people who aren't programmers and don't understand that, this for loop is pretty self-obvious what it does, and, then you're talking about your livelihood. So we want to get in the habit of commenting, and I've been trying to put comments in the code that we develop in class. I'll show you a solution for PA1 with some commenting in it. But more is better, okay? You really can't go wrong with more intelligent comments. Okay, I equals I plus 1 comment, add 1 to I, not a really helpful comment. Okay, it's a true comment, that's what you're doing, but it's not really helpful, right? Why are you adding 1 to I would be more helpful to somebody reading it. Increase the number of inputs, or bump up the size of the array, or something like that. So think about comments. All right, so specific feedback on PA1 submissions. The most important thing in this assignment was to be working with the data structure. So our data structure looks like this. It's a series of nodes. We have a sentinel, which for us was stored at a fixed location in the array, index 0. And the data value stored in here is meaningless. We're only using the sentinel for this field right here, which points to what I'll call the first data node. By the or call it a data node, because technically the Sentinel is a node. It's called a Sentinel node, but it's not a piece of data that's in our list. So this is really the beginning of the list. And the only way you should ever deal with the contents of a linked list like this is to start from the Sentinel and follow the chain of pointers from one node to the next to the next. If you want to search for a number, start with the Sentinel, follow the chain of pointers, but on the way, check each data value to see if it's the number you want. If you're trying to delete something, start with the Sentinel, follow the chain of pointers until you get to a thing that has the data value you want to delete. Okay? So if you wrote code that did a search by going into the array, looping from 1 to 100, and checking each data value to see if it was equal to your number, and checking to see if the valid flag was 1, you succeeded in searching for that node, but you did not use the concept of a linked list as a data structure.
This is an emergency.
Oh yeah, we're supposed to have an unannounced lockdown drill. Sometime
Lock the door and follow lockdown procedures posted near the door. Maintain lockdown until you hear the all clear announcement. This is only a drill. Drill. Lock the door and follow lockdown procedures posted near the door.
Oh, we just did that.
Repeat. This is an emergency lockdown drill. Lock the door and follow lockdown procedures posted near the door. Maintain lockdown until you hear the all clear announcement. This is only a drill.
Same thing. Yeah, English isn't associative. I'm guessing they mean first. Tina lecturing next week.
All clear.
Oh, there we go.
This concludes.
brother teaches high school in Princeton, and they have these lockdown drills, but they have like actors running around in the hallway, like trying to trick you. They'll be like walking on the door saying, let me in, he's coming after me, and you're not supposed to open the door once the lockdown is in progress, so it's like high pressure.
It's kind of scary.
All right. Everyone okay with lockdown drill? The protocol? It seems silly sometimes, but it's like really important because things happen. All right. So yeah, most important thing is make sure you're using the data structure as a data structure. For a linked list, that always means start as a sentinel, follow the links from one node to another. Okay, I'm going to make a chatty Cathy doll that does that. Start as a sentinel. This means that, we always know index 0 in this case is a sentinel node because that's the way we set it up. But is this index 1? Maybe, maybe not. If your list is full, is this index 99? Maybe, maybe not. You really don't know. Because the first node I insert will probably go here, then if I insert a node before it, that node's going to be at index 2, and so this would be index 2. And I might, the first node I put in might be the largest, this last node in the list might be index 1. Right, so we can't use these index numbers to say anything about where something is in the list. Similarly, you never need to check the valid flag. If you're moving through the list and you get to a node, you never need to check to see if that entry in the array is valid. The only thing that should ever be touching the valid flag is get node and release node. Right, that's part of the internal operations of your get node and release node functions. And when we move to PA2, you'll see there is no such thing as a valid flag. And checking the valid flag to see if you're at the end of the list does not work. Right? Everything in the list guaranteed the valid flag is set to 1, assuming that your code was written correctly. Because to get into here, you had to call get node, and that sets the valid flag to 1. So think about that. scanf. We did this a lot in 224. Remember, if you do something like this, and you're saying, okay, I want you to match a character and an integer, the only way to know if you succeeded is to see if r is equal to 2. The only way that you know you failed is to see if r is not equal to 2. Don't see if r is equal to 1, don't see if r is less than 2, don't see if r is negative, because if you fail, r could be 1, it could be 0, it could be minus 1. Right? So if you're trying to scan two things and want to know did I scan two things, say did scanf return 2. If you want to know did it not scan two things, say did scanf return something not equal to 2. Right? If you do that, you won't go wrong. And scanf, like I mentioned last week, it can get a little heavy-handed. If you want to know did the person type in a command letter P, right? Scanning F for a P is a little bit overkill. And scanning for a P followed by a %S can be a little funny, because if you type in a P, this will actually return -1, saying there was nothing to match to the %S. So, string compare to P \n, or check if bracket 0 equals a P, or something like that. Watch the output specification. Most people follow the specification perfectly, so thank you. Success, unsuccessful, node found, node not found, things like that. A few people put in a little bit of extra output, that's okay. A few people put in a lot of extra output, that's a deduction. Printing out a help message every time the person types in a command is not useful, right? Especially if the output that you wanted is here and then it scrolls off the screen because there's a 30-page help message. So follow the output specifications. Make sure you put your name on your program. I'm still getting program submissions that don't have the person's name anywhere. And it may seem silly because I'm pulling down from GitLab, and so that's linked to you, right? But it's your code, put your name on it, right? If you make a painting, put your name on the bottom of it. If you write a great novel, put your name on the front page, right? It's your work, put it on there, and if you're turning it in for a grade, make sure it's got your name on it so the grade goes with your name. All right, indenting, indent your code. I got probably 6 or 7 submissions that were all left justified. Okay, that's an automatic 0 at WSU, at least in some of the classes. Right, they run their code through automatic checkers. That's one thing it checks for is indenting. If there's no indenting, it gets kicked out as a 0. So you've got to indent your code. And the biggest hurdle I see students having almost invariably comes down to not properly indenting. So you've got a return statement and it's inside your while loop instead of outside, and the first time through your while loop, your code exits. And people will spend hours trying to figure out what's wrong with this. The while condition looks right? And it's just that the return was inside the while loop instead of outside. Well, if you're indenting and all of the body of your while loop is moved over, and your return statement is also moved over, you know it's inside the loop. And if it's outside the loop, it'll be indented less. So ask questions about indenting. If you look at the book that I posted, it's got a whole chapter on indenting and code style, things like that. All right. In general, the trickiest part of this assignment is getting things started in the right way and getting them to stop at the right time. Right? So we have a sentinel node, and we have a bunch of nodes, and we have a last node that points to MyNull. So let's say you're searching for a piece of data. Well, you need to use your sentinel to get through the list, but you don't want to check this piece of data. You want to start with this piece of data. And the last thing you want to check is this piece of data, but you don't want to move beyond that because that's pointing to MyNull. And nailing that down exactly is tricky. Right? These are the edge cases, or the fence post problems they're called sometimes. How do I set up my code so that it does all of those things simultaneously? So it doesn't check this piece of data. It does check this one. It doesn't skip over it and start here. It doesn't skip this last piece of data, but it doesn't go too far, which gets a seg fault, or start too soon, which picks up the sentinel. Right? That's part of what you have to figure out based on how you're writing your code. And there's a lot of ways to write these loops, a lot of ways to start off, a lot of ways to use a current and previous or a current and next, ways to end at the top of your loop or return in the middle of your loop. Depending on how you're doing it, you'll have to do different initializations, different conditions, different checks. That's why looking at a piece of code, and we'll look at some code for this, doesn't help you with your implementation. So unless you're going to take a piece of code verbatim, chances are it's going to confuse you more than anything. Right? So you can look at pseudocode, you can look at my examples and get an idea, but ultimately you've got to sit down with your code and with pictures and some test cases and make sure that it's doing exactly what you need. And the more you do that, the more you'll sort of internalize the process of thinking about that. And this will pop up in every program you write. Right? This course, other courses, data structures, non-data structures, there's always these edge cases in the beginning and the end. And you just have to develop whatever your own mechanisms are for figuring those out. And they get easier with practice. Okay, and that popped up in some people's assignments, and that's not a big concern to me. All right, so I will show you some code for PA1. Let me talk about the ODPs first, though, because we've been running free mode on those for a few days. And we have 2 ODPs left for this batch, so 209 is due right now. So, So 207, I think, was where I left you on your own. 206 was new node. I think we talked about that. Okay, so 207, which was last week, you were trying to link 2 nodes together. Right? So you receive 2 pointers to struct nodes, and your function should set the first node's next field to point to the second node. it's literally one line of code, right? Just node 1's next field equals node 2. But remember, n1 is a pointer to a struct node, so we want the thing that n1 points to, right, star n1, we want the next field. So star n1 dot next, that's what we can write by saying n1 arrow next, like this. And it's one line of code, but there's so much that can go wrong here, right? Do we set it equal to n2, or do we set it equal to star n2, or ampersand n2, or star n2 dot next, or what, right? So understanding this one line of code is really huge, okay? n2 is a pointer to a struct node. It's a pointer to the second node of what's going to be our list. So that's n2, this is n1. And they're nodes, so there's a data field and a next field. And the way to think of it, if this is node n, this is n arrow data, this is n arrow next. Right, that's the name for those two pieces of the structure. And n itself is the address of this thing. So we want to make a list, we want this to happen. Well, we always draw the arrow pointing to the side of this top box, right? But what we really mean is we want to point to the beginning of this node, right? That's what n2 is. It's an address. It's a big number, which says where is this stored in memory. We could technically, say the address of n2 arrow data, but don't do that, because that's not guaranteed to work. But that's kind of what this picture looks like, right? But really just n2, that's the address where this thing begins. So n1 arrow next equals n2 sets that up exactly. So 208, which was the weekend ODP, we're building a linked list. So 3 nodes, x, y, z, and you want to build, make a sentinel node, and then chain these 3 nodes together, and then return a pointer to the sentinel node. So it's kind of like an extension of 207, except you have to create these nodes yourself. And then you have to set the data values equal to x, y, and z. So it's more than one line of code, but it's similar to the code that we posted last week. Declare 4 pointers, initialize each of them using malloc, set the data fields equal to x, y, and z, and then chain them all together. Have the sentinel's next field point to n1, n1 points to n2, n2 to n3, and n3 to done, and then return the address of the sentinel. All right, so today's ODP is going to edit a linked list. So you're given a pointer to a node, and there's no sentinel in this case, okay? It's just 3 nodes. You're given the address of the first one, it points to the second, it points to the third, and your goal is to do whatever you have to do to make that middle node disappear from the list. Well, what does that mean? It means basically take this first node's next field and change it to point to whatever this third node is. Well, how do you find the third node? It's the second node's next field. And how do you find the second node? It's where the first node points to. So there's a lot of ways to code this, but basically start with PTR, look at its next field, that's this. Look at that node's next field, that tells you where this third node is stored. Now change PTR next to be equal to that address. And I don't think I require you to free this middle node, but you can do that if you want to be nice. All right, so that's today's ODP, yeah.
So I'm always confused when I'm supposed to be allocating for a structure and when I shouldn't.
Yeah. So like in here, my function is not being passed any nodes, it's just being passed a few integers, and I'm being asked to create a list of nodes. Okay? That's your first hint that you're going to want to use malloc. Okay? But let's take a look at this one. Here I'm told I'm being given 2 nodes, and I want to have one point to the other. Right? There's nothing in that description that says, and create a new node and do such and such with it. So in both cases, right, I might be passed a pointer to a struct node, but if that already points to an existing node, I don't want to do malloc. Okay? And one thing that I'll see sometimes is something like this. So let's say this is like, add something. Let's say you pass a sentinel node into this thing. So I'll see this combination of code sometimes. The person says struct node star temp. Temp's going to be a temporary node pointer. They're going to use this to move through the linked list. And then they say temp equals malloc, which creates a chunk of memory and has temp point to that. And then somewhere in their code, they're ready to move through the list, so they set temp equal to the sentinel node. So temp is now a reference to this first node in the list. Bless you. Well, you've not only done extra work, you've created a memory leak. Because what you did right here was you said allocate a block of memory and have temp point to that. And now you're saying, oh, I changed my mind, have temp point over here instead. And what's happening with that memory block there? Nothing's pointing to it anymore. It's been allocated, there's no way to free it because you don't have a pointer to it. And there was no need to do this because you weren't planning to use temp until you gave it a value, and you're giving it a value right here. Right? So this is totally extraneous, it's extra work, it's extra time, and it creates a memory leak. So if you're making a node, use malloc.
So then, in like real life applications, right? So for like in 224 we did like the index. So it was like someone was trying to do it with dynamically malloc working, and that wasn't very efficient. So when do we know which is more efficient to use, like straight up?
It's going to be more efficient to not use malloc. Okay, but if you don't know how big something needs to be ahead of time, that's when you want to do it during runtime, which is what malloc does. So if you were reading in something into a big array, but you don't know if I need this array to be 100 or 100,000, right, that's a case to use malloc. In a linked list, we don't know if our list is going to have 5 nodes or 500 nodes. So we can't have, struct node star A, comma B, comma C, comma D, comma E, and list all of these things ahead of time, right? So that's a case where we would definitely use malloc. But it really kind of depends on the problem. If you can visualize a way to do it easily without malloc, then it's probably right to do it without malloc. Unless, an assignment says you must use malloc. But the more we work with this, and we're going to be mallocing everything else that we do in this course, the more we work with this, I think the more that intuition will develop. All right, so let's talk about PA2. We'll go through PA1 afterwards or tomorrow. So this is going to look very familiar. So PA2, you're going to implement a linked list. Your node structure is almost exactly the same, except instead of next being an integer, it's now a pointer to a struct node, which is this structure. So it's a genuine data structure element. We can think of next as the memory location of the next element, right? It's kind of like an index in memory. Or at the end of the list, it's going to be null, N-U-L-L, instead of my null. So that's one change. Next is a pointer to a struct node. Second change, we're going to use null instead of my null. And null is set up in standard io.h to be the right thing. And it's not -1, it's actually 0. Okay, your main program is going to declare a struct node star list instead of a struct node list bracket 100. Okay, these are both arrays of struct nodes. But when we say struct node list bracket 100, we're saying this can only hold 100 things. Like this, it's just a pointer to a struct node. Okay, so you declare lists slightly differently. And then you implement the following functions. So init, we talked about this the other day. This is really just a call to malloc. Okay. So init should create a new struct node and return its address. Okay. So this gives you a sentinel node. So call malloc to the size of struct node, not struct node star. Set the next field of it to null, indicating that it's not pointing to any nodes, and return its address. Okay, this is similar but slightly different from PA1. All right, add exactly the same as PA1. Takes a struct node star and takes an integer, searches a list starting with a sentinel moving forward, finds the right spot to insert this number, makes a new node with that number as a data value, and adjusts the links before and after to chain them all together into a list. Print exactly the same thing, print the nodes. By following a list, they will be in sorted order automatically. Print them out all on one line, spaces in between, new line at the end. Delete takes a number, searches the list for it, removes it from the list. Search searches for a node, returns 0 or 1. Okay, so those are all the same behavior and almost exactly the same code, definitely the same algorithm as what you did in PA1. Okay, assuming that you obeyed the data structure in PA1. Main program, no changes. Okay, so if there's any discrepancy here, it should do the same thing as PA1. I just added some more information. With the one difference that when you exit your program, you should free all allocated memory. Okay, so no memory leaks. So don't just exit at that point with a return. You got to do something to free the memory, which we'll talk about how to do. And it's pretty easy. It's no harder than printing. You just basically move through the list and you free the stuff behind you. So we'll pseudocode that. Deliverables, same as before, right? Put it in the GitLab repo named linked list 2. A bunch of people have already got a linked list 2 up on GitLab that I have access to. Thank you. That makes things really a whole lot easier. So that's the same, basically. So, and you've already done pieces of this, right? By the time you finish today's ODP, you've written code that can move through a list of struct nodes where the next field is a pointer to a struct node. That's enough to do your print function. That's enough to do your search function. Okay, and if you code up print and you code up search, and you can make a linked list using today's ODP, right? The code you write will build you a list with 3 numbers in it after the sentinel. Yesterday's ODP will build you a list with 3 nodes after the sentinel. You can pass that to your print function and see if it prints out your 3 nodes. You can pass it to your search function with different numbers and see if it searches. Search for the first, the last, the middle, search for numbers that are bigger and smaller than anything in there. And once you've written the print and the search function in this new paradigm, writing the add function is pretty much a translation from PA1, because you'll start to see how the code you wrote using the array translates into code using these pointers. So let me pause there. Let me run through some code for PA1, and then we'll come back to looking at PA2 and the quizzes. I got to check the dates on the quizzes. If we don't have a week for quiz 1, I'll push it back. But we'll get to that tomorrow. All right, so So PA1 code, so this is modularized, does not have to be modularized. So here's my main program. I like small main programs, right? Main programs can be thousands of lines, and that's kind of overwhelming, so I probably have more comments than I have actual lines of code in here. I declare my list to be an array of struct nodes. I have my favorite buffer that I'm just going to use to hold temporary input. I initialize the list, right? That's just calling the init function. I print a prompt, and then here's my main loop. 4 lines. Call fgets to read in a buffer. If it returns null, that means the person hit Control-D. Well, I didn't ask you to do that. You can just exit with the X command. So this could be an infinite loop. But I pick up null, which means the person hit Control-D. Assuming they typed in something, it's now stored in buffer, and I have a function called process, which takes the list and the string containing the command, and it does whatever the command says it should do. And if there's errors, it'll print error messages. If it's an add, it'll do the add. If it's a search, it'll do the search and give you the results, and so on. Bless you.
Thank you.
And then it returns a flag. And the flag is, if the person typed the X command, process returns 0. Otherwise, it returns non-zero. So in here, I can say, if process returns 0, then I just exit. Otherwise, I print a prompt, I go back to the top of the loop. So there's nothing happening in here. This is just a wrapper, right? But it lets me keep my main program simple. Process is kind of the workhorse of the string processing, but it doesn't actually do any of the actual list manipulation. That's all done by other routines. And I have a myStuff.h, which is just defining the structure and the symbol myNull and prototyping the functions. So there's myNull, there's struct node, there's the prototypes for the functions, and I throw in standard I/O, so I don't have to include it over here. So process gets a buffer, that's the command, right? And I switch on the first character. And if the first character was an I, then I say, okay, is this an I followed by an integer followed by anything else? So if scanf returns a 1, it means it found an integer, it didn't find anything else. That's exactly I followed by an integer. And I mentioned in class, I'm not going to worry about if you said something like I 2.5, it'll insert a 2, that's fine. Okay? But you want to catch if you say insert haha, right? Don't just insert a random number. Notice that it doesn't have an integer, so that's why we're checking the return value from scanf. If it returns a 1, then num is the number we're trying to insert, search the list. If that number is in the list, print a message saying node already in list, otherwise call the add function. And I've got that in an if statement. If it returns success, then I print out success, otherwise I say no memory available. If all of this fails, so this is the end of an if statement that started up here. So I know my first character was an I, but if scanf did not return a 1, it means it was followed by something other than an integer or nothing at all. So I call this function usage, which prints out my help message. I didn't want to type that a million places in here. And then break takes me to the bottom of the switch statement. And every statement is basically like that. So if it's a P, I just check to see if it's followed by a new line. If it is, I print the list. Otherwise, I print a usage message. If it's an S, same thing. Pick up the number, make sure there's a number, and either print out the return of comparing the search value to 1. So this is just a fancy if-else statement. So it says if search returns a 1, print out the word found. Otherwise, print out the words not found in place of this %s. And same for D, same for X. If it's an X, returns 0. If it's none of those, print out a usage message. If it was any of these above, when I come out of the switch, I'll say return 1, and the main program will continue with its while loop. All right, so we'll go through the rest of the code for that tomorrow, and then we'll start, go through the quizzes, and we'll start digging into PA2 pseudocode.